Today, I'm going to talk about refraction. There are actually a lot of similarities between reflection and refraction, so you should be familiar with my video on reflection. Refraction, in its most basic form, is when light passes through a surface. This is opposed to reflection, where light bounces off of a surface, or absorption, where the surface gains the light energy. Like reflection, refraction obeys Snell's law. Reflection, however, uses a simplified version of the law. The full form states that the index of refraction of one material times the sine of the incidence angle equals the index of refraction of the second material times the sine of the exiting angle. The incidence angle is the angle of the incoming light with respect to the normal line. Similarly, the exiting angle is the angle of the light as it exits, with respect to the normal line. The normal line being the line that sticks straight out, perpendicular to a surface. The index of refraction is a property of the material. Each material has its own index of refraction, and it relates to the speed that light travels through the material. The higher the index of refraction, the slower light travels through the material. Only light passing through a material with an index of refraction of 1 travels at the speed of light in a vacuum. This is the maximum speed of light, 299,792,458 meters per second. As you might expect, only a vacuum has an index of refraction of 1. According to Snell's law, when light travels between two materials that have different indexes of refraction, the light bends. If it goes from a high index of refraction to a low index, it bends away from the normal line. While if it goes from a low to a high index of refraction, the light bends towards the normal line. Interestingly, in the barrier between materials, it is possible for no light to pass through at all. This is known as total internal reflection. If light passes from a higher index of refraction to a lower index of refraction at certain high enough angles, all light is reflected. This can be seen with Snell's law. If we bring the second index of refraction over to the other side, we see that if the sine of our incidence angle times the first index of refraction divided by the second index of refraction is greater than 1, we cannot have an exiting angle. This is because we can't take the arcsine of a number greater than 1. There is also the critical angle, which is the angle where light just starts to be totally internally reflected. This occurs when our incidence angle gives the sine of our exiting angle a value equal to 1. As such, we can find the critical angle by taking the arcsine of the second index of refraction over the first index of refraction. Note, we cannot have total internal reflection if we go from a low index of refraction to a high index of refraction. You can see this if you try to find the critical angle. We end up taking the arcsine of a number greater than 1, indicating it is impossible. Possibly the most important aspect of refraction is how it relates to lenses. However, first, I need to discuss what happens when light passes into, and then out of, a material. Let's say that a ray of light passes through a rectangular piece of glass. When the light enters the glass, it is distorted a bit. However, when it leaves the glass, it is distorted in the exact opposite manner. This can be seen with Snell's law. When it passes into the glass, it exits at a certain angle. It then travels in a straight line to the other side of the glass. This means that this incidence angle is the same as that exiting angle, causing it to distort oppositely. Of course, this only works when the normal lines of both sides of the glass are parallel. The light is distorted even more if the normal lines are not parallel, as is the case with lenses. There are two types of lenses, converging and diverging. Converging lenses have thin edges and a thick center, while diverging lenses are the opposite, a thin center and thick edges. Each distort light, albeit in different ways. Converging lenses cause the light to come together, or converge, while diverging lenses cause the light to separate, or diverge. As with mirrors, we want to see where the light ends up after interacting with the lens. For this, we use the object, which is what the light originally bounces off of, the lens, which is what the light passes through, and the image, which is what the reformed light creates. Mirrors and lenses actually have a lot in common. In fact, 3 of the 4 light paths that were used to analyze mirrors apply to lenses. I will get to those in a bit, but first, there are a few notable differences. Because they are 2 approximately spherical pieces of glass smushed together, lenses have 2 focuses. The focus is the point where any light coming from infinity will be focused. Additionally, because light actually passes through lenses, images on the side of the lens opposite the object are now real, while images on the same side of the object are virtual. Because of this, it no longer makes sense to define one side of the lens as positive or negative. However, the mathematical features are still the same, as I will get to later. To find where the image is after the light passes from the object and through the lens, we need to trace out the path of various light beams. Due to the distorting nature of lenses, most beams will be hard to follow. Luckily, there are 3 easy-to-analyze light paths. Now quickly, before we get to those, I need to introduce 2 lines, the axis and the center line. The axis is an imaginary line sticking straight out from the center of the lens, perpendicular to the lens. The center line is the line splitting the lens in half lengthwise. Since lenses are thin, all distortions are approximated to take place at the center line. Both of these lines are imaginary, but aid in lens analysis. Nevertheless, the first path goes from infinity, parallel to the axis, through the second focus. Since light paths follow a reversible process, the second path goes from the first focus to the lens, and then parallel to the axis. The third path just passes straight through the center of the lens. At that point, the sides of the lens are approximately flat, so the light isn't distorted at all. Despite the fact that I made these diagrams for converging lenses, these paths apply to both converging lenses and diverging lenses. The only difference with diverging lenses is that, due to the opposite curvature, the foci are switched. So, counterintuitively, the second focus for a diverging lens is actually in front of the lens, while the first focus is behind. With this noted, all 3 paths can be applied to find the image without issue. With these 3 paths, we can find where any image will be located given the location of the object and the 2 foci. As with mirrors, the exact positioning and height of the image will depend on those of the object, but there are 4 general situations with lenses. 3 of these are for converging lenses, while there's only 1 for diverging lenses. Now, I should mention that since the glass in lenses is approximately spherical, it has a center point, which is at the center of the sphere. Our first situation is if the object is behind the center point in a converging lens. We find the image by tracing out the 3 paths. Parallel to the axis and through the second focus, through the first focus and parallel, and directly through the center of the lens. Now, when we find the image, there are three general characteristics. It can be either upright or inverted, real or virtual, and larger or smaller. Since the image is on the opposite side of the axis, it is inverted. And since the image is where the light actually is, it is real. The image is also smaller. Therefore, any image behind the center point for converging lenses will be inverted, real, and smaller. If we now move the object in front of the center point, but keep it behind the focus, we have our second situation. We draw the three paths, and see that our image is still inverted and real, but now it is larger. For the third situation, the object is now in front of the focus for a converging lens. Drawing the three paths, we see that the image is now on the same side of the axis as the object, making it upright. Likewise, the image is on the same side of the lens as the object, making it virtual. The image is also larger. These same three characteristics are used to describe the diverging lens situation as well. In drawing the light paths, as in the previous situation, we need to draw virtual lines. These are lines extending backwards from the light path after it passes through the lens. The light does not actually go in this backwards direction, which is why these paths are called virtual. After drawing the paths, we see that our image is virtual, upright, and smaller for diverging lenses. This is true regardless of where the object is relative to a diverging lens. It should be noted that these four situations parallel those four results with spherical mirrors. As I have mentioned, there are numerous parallels between spherical mirrors and lenses. In fact, aside from the fact that mirrors reflect and lenses refract, converging lenses are identical to concave mirrors, and diverging lenses are identical to convex mirrors. Because of these similarities, the mathematical equations used with mirrors apply to lenses as well. The first of these states that 1 over the focal distance, f, is equal to 1 over the object distance, s, plus 1 over the image distance, s prime. The object distance can be measured outright, while the focal length needs to be found using the lens maker's equation. Since the two pieces of glass in lenses can have different curvatures, and thus different radii, we cannot directly relate the focus to the center point like with mirrors. The lens maker's equation accounts for these differing curvatures to give us our focal length. The equation states that 1 over f equals the index of refraction of the material, minus 1, times 1 over the radius of the first piece of glass, minus 1 over the radius of the second piece of glass. Radii in front of the lens are negative, while those going behind the lens are positive. Going through these calculations, we can find the focal length for any thin lens. We find that, like with convex mirrors, diverging lenses have negative focal lengths. Similarly, a negative image distance tells us the image is virtual. A positive image length indicates a real image. With the focal length and object distance found, we can use the first equation to find the image distance. If we then measure the object height, we can use the magnification equation to find the image height. The third equation states that the magnification equals negative s prime over s, which also equals the image height, y prime, over the object height, y. If the image height is negative, then it is below the axis, indicating the image is inverted. If y prime is positive, the image is upright. Additionally, if the image height is more than the object height, the image is larger, and vice versa if the height is smaller. Using these three equations, we can describe the position and height of our image. All of these similarities between spherical mirrors and lenses are quite convenient, as we only have to remember one set of light paths, one set of characteristics, and one set of equations. Perhaps the parallels shouldn't be that surprising, as reflection and refraction are both part of geometric optics, and all of these principles follow from Snell's law. Nevertheless, hope you enjoyed it, hope you learned something, and see ya.